it was supposed to be a cycle from when we did it, but then there was the lab that you guys didn't write up yet. And that I thought we decided was due like yesterday or today-ish. So there's the, okay. So there's the collisions lab. That's the one where Priya came and said that nobody did it. And could we possibly extend the deadline? Yeah, we had a conversation about that yesterday. And then there's the rotational inertia lab. There were two momentum labs. No, you guys turned in the first one, the impulse momentum one, with the elastic thing. This is where you had the two cards that stuck together and moved off together. Sure. What was the momentum impulse one? No, this can just be data and questions because this should be a formal lab report. So let's say this is due Friday. And this is due Monday. All right, can we do that? Okay. Wait, Gianni's still confused. Number 19, Zoe says it is. Yeah. But you made a collision. So it's momentum energy. Okay? So everybody knows what they're doing. Everybody's got it. We're all good and be good. Everybody's going to turn everything in on time. All that stuff since I've given you weeks and weeks to do it and new trimester and all that jazz. Sari. Oh, you're never going to have the homework done by Friday. It's long. You're never going to have it done by Friday. I can tell you right now. And I believe I said that was negotiable. Let's let the homework be due Tuesday. It's chapter 11, right? Okay. Just because we're not going to finish. Yeah, no. We may finish before then, but yeah, but no. Exactly. And then when I was looking at them for you. So, okay. So everybody understand when everything's due now. We're all good. We can move on with our lives. Gianni's going to write it down. She will be our recorder. Okay. Although it's right here, and Maddie could watch the recorded class, and it's right there. I will try to update the portal. Okay. All right. You can do some of the homework already. What did I say it was, though? 4, 5, 6, and the last two? 3, 4, 5. Okay, and then you'll be able to do a lot more after we do cross product today. Okay. All right. So everybody got this? Everybody good? We can move on and actually do class. Okay. So we were talking about making torque into a vector. And we had our axes. And this is one of those situations where you do not get to choose where x, y, and z are. And unlike math, z does not come out of the board. Okay, this has to work this way for a reason that will become apparent by the end of class. And then I have some particle A that's located some distance r from the origin. There's some applied force F that's acting at some angle phi. Doesn't really matter where. And then I say that the torque is equal to R cross F. And this is all things that we wrote down yesterday. I can still find the magnitude of that torque as RF sine phi. But what we didn't get to talk about was the fact that torque is now a fully fledged, bona fide vector when we write it this way. Okay? But note that up here, we are multiplying two vectors, which we've never done before, quite this way. All right? We've multiplied two vectors together with a dot in the middle, and what do we get? When I multiply two vectors, but I take their dot product. I multiply their magnitudes and I take the sine of the angle between them, but what kind of quantity do I get when I take the dot product? I get a scalar, okay? And note here that when I take the product of these two vectors with a cross or an x in the middle, I am actually getting a vector back. So this is going to be a new kind of multiplication. But let's talk about the direction of tau first. And this is going to be another right-hand rule. Different right-hand rule, but another right-hand rule. So what I do is I take my two vectors. So in this case, here's vector R, and here's vector F. And I redraw them, or I imagine them to be tail to tail. And they are, as we said, separated by some angle phi. So what you're going to do, make sure everybody's done writing because everybody needs to do this, is you're going to take your right hand. It has to be your right hand. It doesn't matter if you're left-handed, it has to be your right hand. Okay? Okay? You're going to take the fingers of your right hand and you're going to put them in the direction of the first vector, which in this case is R. Okay? You're going to bend your fingers naturally into the direction of the second vector, which is F. And then you're going to stick out your thumb. And the direction that your thumb points is the direction of the product. So in this case, the torque comes out of the page, perpendicular to the page. Yeah, stick your thumb out. Okay, so in this case, the torque comes out of page, perpendicular. Couple of things to think about. Number one, the torque will always be perpendicular to the plane created by R and F. Which means when you're taking Calc 3 someday, or, oh, was that awful class? Yeah. I took some other class though where I needed to do this, but I think it was Calc 3. And you need to create a vector, or you need to create something that's perpendicular to a plane, find two vectors in the plane, take their cross product, and now you have the equation for something that's perpendicular to the plane. Okay? It's a math tool, even though we're using it in physics. Okay? Pretend for a minute that instead of torque being R cross F, torque is F cross R. So now, again, I take the fingers of my right hand and I put them in the direction of my first vector, which is F. I naturally bend them into the direction of R. And which way does my thumb point? Into the board. Well, you have to move your hand is the trick. Because I could put it like this, but I can't make my fingers bend into R. So I have to flip my hand over, and then I can bend my fingers in the direction of R. And in this case, tau goes into the page. Again, perpendicular. So what this is telling you is that F cross R is not equal to R cross F. So vector multiplication, or the cross product, which is what we're talking about, does not commute. You will get a different answer. We shall get there in a moment. Okay, I want to talk about one more thing. And then we'll talk about how to calculate it. Okay. So every time we add a layer of complexity, we want to make sure that it's consistent with what we've done before. So if we go back and remember what Newton's second law is for rotational cases, which was tau is equal to I alpha, okay, and then if I consider a wheel or a cylinder or whatever it is that's rotating, okay, and it's going to rotate this way, and I consider, say, a point on the rim that's located at some distance r, and if I'm accelerating so that there's a force that's making my wheel spin faster and faster and faster, okay. So number one, if my wheel, and this is my omega, if my wheel is spinning faster and faster and faster and faster this way, which way does alpha point? Alpha. It's your other right-hand roll. Your right-hand screw roll. It comes out of the page, right? Because this is the direction of the acceleration. So alpha is perpendicular to the page coming out, right? Now, if we look back at Newton's second law again, tau net and alpha should be in the same direction. But remember that the other way to write the torque is R cross F. So again, sometimes you got to turn your whole body. If I put my hand in the direction of R, my right hand, and I naturally curve my fingers into the direction of X, which way does tau point? Perpendicularly out of the board. So this means that my equation up here, at least as far as the vectors are concerned, is consistent. Okay, no matter how I look at it. So we didn't do anything wrong in the past. We just had it simplified. Okay. All right. So hopefully you all read parts of chapter 3 that you were supposed to read about cross products or vector products. And so let's talk about that. You need me to go back? Okay. All right. So we're going to consider two vectors. Vector A, which has components like this, and vector B, which has components like that. Okay. And we're going to take the cross product. So even though the cross product or the vector product doesn't commute, I can still distribute. It still obeys those rules of math. So what I can end up with is AXI crossed with BXI plus AXI crossed with BYJ plus AXI crossed with BZK, and then do the same thing for the second term and the third term. Okay, and then end up with 9 terms. That's an awful lot to write down. But if you remember when we did the scalar product or the dot product, there was a shortcut we could take. Because I'm doing some of the same multiplication over and over again. So let's remember a couple things here. If I had two vectors, C and D, and I wanted to find the magnitude of their cross product, what would I write? If it was RF cross, if it was R cross F, what's the magnitude of that vector? RF sine phi. So if I just have two random vectors C and D, it would be CD times the sine of the angle in between them, right? No, dot product has a cosine. It's a similar formula. Okay. So let's see if we can simplify our math up here a little bit. If I take I cross I, and I want to find the magnitude of that, say. What's the magnitude of I? 1, because what is I called? It's a unit vector, and what does unit mean? 1. Times the sine of the angle between them. And what's the angle between I and I? 0. And the sine of 0 is 0. So if I have two vectors that are parallel to each other, and this is important too, their cross product is 0. So how about J cross J? Which is what? 0. How about K cross K? 0. So that knocks out 3 terms right there out of my product up there. Okay. So I've also got a bunch of other things that are going to show up. So I'm going to make myself a little axes over here. And remember, I have I, J, and K. And that I comes out of the board, which is very important. So what if I take I cross J and use the right-hand rule? What am I going to get? Yeah, I is coming out of the board, J is in the board, and my thumb points in the direction of their product, which is K. Correct. It is directional because the reason it's called a vector product is because you get a vector at the end. Yeah. All right, so the first time I drew 3-dimensional vectors back in chapter 4, if you were paying attention, and I might have had my back to you, I always have to go, okay, I cross J and up. Because the reason why X comes out of the board is so that I cross J equals K in physics. Okay? With me? It's just the way it works. Well, if I'm going to draw it over here because I don't want to muddy the waters. In math, we would often draw it that way. And I guess it would, it just seems wrong. I guess it just seems wrong. It is wrong. It's not the way we do it in physics. We do what you want in math, but not here. Okay, so let's try another one. J cross K. Sure, what's your question? We'll get there. But yes, we do. So J cross K. J cross with K. That's why it's the right-hand rule. If it makes you happy and you don't screw it up. That's kind of the whole, you can do it any way you want until you do it wrong, and then you have to do it my way. K cross I first. Nope. K crossed with I. K. I comes out of the board. J. So whoever said it is right. We've got it because the multiplication doesn't commute, you have to calculate J cross I separately. So here's J, bend my fingers into I, and what's that going to be? Negative K. And then we also want to do K cross J. Because it's going to be K, bend my fingers into J, my thumb goes into the board, negative I. And then I cross K. That one's a little tough. Yep, I mean tough to do with your hand, not any harder than any of the others. I comes out of the board, you bend your fingers up for K, and you're in negative J. I would not memorize these. I would memorize the right-hand rule and figure them out. Okay. In many situations, your vectors will, well, we'll talk about that. Okay, so now we can apply all of these shortcuts to our vector up here. No, not at all. Okay, so let's see. I'm just going to copy it and paste it because it makes my life easier. Okay. So what you have to remember is that IJ and K are just the directions that go with X, Y, and Z, but there's an actual component, an actual numerical value that goes in front of it that you don't want to lose when you do this. Okay? But we're still going to be doing like I cross I and stuff, but yeah, that would be equal to 0. All right, so let's just do this so that we remember. So AXI cross BXI is going to give us 0. Okay? AXI crossed with BYJ is going to give me what? AX. Yep. Okay, and this is the part where you don't want to forget to bring those coefficients with you. Okay. And then AXI times BZK gives me yep. That's okay. All right. And then we start with the second term. So we have AYJ crossed with BXI. Negative K. AYJ with BYJ gives me 0 because the J's are parallel to each other. And then AYJ with BZK okay. And then AZK times BXI AZK BYJ right, going to give us negative j. And then azk times bzk is 0. Right, you said it, Sarah, didn't you? I thought I heard you. Okay. So then, of course, what you're going to do is bring together the terms. Oops, that's not it. Did I lose? Oh. What? Oops, wait a minute. I wrote something wrong. That should have been an I. Make sure I made a mistake. Wait a minute. What's wrong here? No, that's a J. That's an I. Okay. Sorry. All right, so you're going to want to take and combine all the terms that are in front of the same vectors. And if you're a person who finds patterns in things, there are all kinds of patterns to find here. Okay? And if you need to use those patterns as a mnemonic, you can. However, there are an awful lot of letters there and an awful lot of places to make a mistake. In the real world, or the world in which you will be tested, it would be odd for you to have all three components of both A and B to be non-zero. So really, I'm going to show you another way to do this, but really it's better to just write it out and write out this step and then just do the math. Okay, do the multiplication. Even if you have to draw, the little axis over here and cross with your fingers and stuff. So, yep, we'll go back. Don't worry. Okay. Okay. Well, I was going to do one more thing and then take a break. Okay. All right. So there's another way to calculate this that's related to matrices and finding a determinant-ish. Okay, so it works. So this is kind of an alternative technique. Oh yeah. Alternative technique. Yeah, the letters. There's a C there, and the R and the N got all mixed up. Yeah, it's a problem. I totally agree. Okay. So I'm still taking A cross B, and A and B still have the same components that they had before. But what I do is I draw them, or I write them as a matrix. Okay. You still write the first vector in the second row and the second vector in the third row, you can't change the order. Okay. Good, just lines. Okay. So if you want to find the I term, you block the row and the column that have I in them. And then you multiply this way minus multiplying that way. So you're finding the determinant of this little 2 by 2 matrix here. So it's going to be AYBZ minus AZBY. J is a little complicated. J, you have to rewrite the term over there. But it's not. Yeah. Okay, so again, if you want to find the J term, you block the column and the row that have J in them, and then you go this way minus that way. So it's AZBX minus AXBZ. For K, now you can just go back and again block the row and the column, and it's this way minus that way. So it's AXBY minus AYBX, which I think is exactly what we got before. You can't do that for J. You could, but you have to remember there's a minus sign, an overall minus sign, which I find to be very annoying to remember. I think it's just better to write the I term. It is, but sometimes this will make sense. If I had like all three components non-zero of both vectors, I would do it this way. But if I had even 1, 0, the other way is not so bad. Okay, so that's kind of the other way of doing it. So why don't you guys take a break for a couple minutes, and then we'll come back and we'll do a problem and do some other stuff. All right, so let's try some sample problems that show us how we can play with this new technique. So let's do page 322, number 23. Somebody read it for us, please. Oh, no, that's not it. It should say force. Okay, so let's try 23. Okay, so we'll come back to part B. We are going to do part B. But for part A, we're just worrying about the origin. So what's our formula for torque? Tau equals R cross F. Okay. I alpha, RF sine phi. Yeah. But I want to find the vector, and I want it in unit vector notation. But what does R stand for in this problem? Well, Up here it does, but what I should have said is in this formula, what does R stand for? Yeah, but when we first introduced torque, we called R something for one thing. It was the moment arm. And the moment arm measures the distance between what and what? No. What did you say, Casey? Okay. I couldn't hear what you were mumbling. Go back and look. What does the moment arm measure? Probably the first day of chapter 11. It might have been wherever we introduced torque, the first day of torque. You're right, it probably was chapter 10. Okay, so it's the distance between the rotational axis and where F is applied. So if the problem says that we're looking for the torque about the origin, then the origin is the location of the rotational axis. So that means that in this case, the position vector R is the same as the R that we use for our moment arm. Because R, the position vector, is measured from the origin to wherever the particle is. So part A can be pretty simple. So torque is going to be R, which is going to be 0.50 J minus 2.0 K, crossed with F, which is 2.0 I minus 3.0 K. It's one of the few times where I let you not write units, just because it's kind of, there's too many symbols. Okay. And then there's, of course, two different ways that we can evaluate this cross product, right? We can just do it term by term. So if I do J times I, what do I get? Okay, so that's going to give me negative 0.5 times 2 times K. Okay, J times K gives me I. So that gives me 0.5, but remember there's this negative sign here. And I have to take that negative sign into account somewhere. I like to attach it to whatever the coefficient is of the unit vector. You can do it You can attach it to the unit vector itself, but I find that makes things more complicated. Okay. And then I've got k crossed with I, which is going to give me j. Well, no. K crossed with I gives me j. But I've got a -2 and a +2 that I'm multiplying. And then finally, I have k crossed with k, which is going to give me 0. So this tells us that our torque is going to be -1.5 Newton meters I minus 4 Newton meters J minus 1 Newton meters K. Okay, just by doing the math. Yeah. Okay, but let's practice the other way of doing this too. Okay, with the matrix. And see if we get the same thing. All right, I'm going to go to a new screen here. So this is going to give me I, J, and K. The R vector is 0, 0.5, no. Yeah, 0.5, -2. The F vector is 2, 0, -3. Okay. So again, if I want my I term, I block the row and the column that has I. So that's going to give me 0.5 times -3 minus -2 times 0. And then I've got to write, yep, my I term again out here. Because when I want to find the J term, again, I block the row and the column that J are in. And I go this way, which is going to give me -2 times 2 minus this way, which gives me 0 times -3. And then K again, I block my column and my row, and I have 0 minus 0.5 times 2. And that's still going to give me -1.5 Newton meters I minus 4.0 Newton meters J minus 1.0 Newton meters K. Almost. Okay. All right, so we good? We got both those types of ways of doing it. It really just depends on the situation. But now we have part B. And in part B, our axis of rotation is somewhere other than the origin. But R is supposed to be the distance between the axis of rotation and the object. So if I draw my axes here again, X, Y, Z, okay. I have the location of my particle and whatever its position vector is. Who what? Oh, nope, it's an R. But I really want to take the torque around a different point that looks like that I'm actually going to call R prime. And R prime is going to be over here somewhere. You assume that all vector, that the beginning of all vectors are the origin, so it's a position vector. I'm just writing it different to make things go faster. Okay, so my axis of rotation, or my R vector for my tau, and I'm going to write it this way, tau, I'm going to call it is R nu cross F. R nu looks like this. R nu is the new moment arm, but how do I make that be, how do I write that in terms of the things that I know? Yes. Yes. It's that new position, that point, the position of that point. Not dealing with force yet. I just got to figure out what R nu is. Eventually, but I need R nu first. I know what F is. It's the same as it was in part A. Prime. Look at the vector picture. You know how to add vectors. No, there are no 90-degree angles. I mean, there might be, but it doesn't matter. No. No, you can't. I want you to tell me what R nu, well, I don't want you to just tell me what R nu is equal to. I want you to tell me how to find R nu with respect to the two vectors that I know, R and R prime. So R is equal to what, Casey? What does it mean that it's the resultant? What do I have to do to get the resultant? Oh, you're absolutely right. I just want you to write it as an equation. Tell me as an equation. Yes, you do. You do. If you're going to tell me that R is the resultant of A and B, R is equal to what? Help her, Priya. No. Yeah, right? Right? I mean, that's what was in your head. Okay, so R is the resultant of R prime plus R new. Yeah, well, but if you can't say it, then it doesn't count. Okay, because if you look at it, R prime and R new are lined up tip to tail. R connects the leftover tail to the leftover tip. Chapter 3. It all builds. It's all going to come back and bite you in the butt. I'm telling you. Okay, so of course what I really want is R new. So that's going to be R minus R prime, right? And what was R? I've lost R. 0.5 J minus 2K minus 2I minus 3K. Just turning the position of that point into a vector. Okay, so we can do this math. This is easy, right? So that's going to give me negative 2I plus 0.5J plus 1K, I believe. Yeah, now that I want to find the torque, R new cross F. So I've got my R new. And what was F? 2I minus 3K. Is that right? Okay, so you tell me what the answer is. I shall. And anything curious about your answer? I would relook at your J. I would look at your signs. What'd you get, Casey? I'd look at your eyes in case because you did something weird. Yes. Whereas Gianni's signs are right, but not all of her magnitudes are. And Casey flipped some stuff. Yeah. But it's not. You did the matrices wrong. Did you write the I column over? So? You didn't. How did you get what, so? Because you did the cross products wrong. Zeri. So when you go this way, so you do I cross J equals K, J cross K equals I, K cross I equals J. It's a cycle. So because you're going counterclockwise, you're positive, right? Because it's a counterclockwise thing. If I go this way, I get I cross J is negative K, right? If I go this way, K cross J is negative I. If I go this way, J cross I is negative K. So it's all this cycle. You just have to know which way is positive and which way is negative.